Hello everyone. As you probably remember, we have finished more than half of the last chapter of 11th standard, that is the chapter Waves. Now we are going to continue from there and finish our 11th standard syllabus and then move on to the 12th. So before we can finish the Waves chapter, here is a quick review of what we have seen so far. Frequency of the wave depends on the source, but the wave velocity depends on the medium. These are some of the basic formulas. V is equal to f lambda. V is the wave velocity, f is the frequency, lambda is the wavelength of the wave. F, again, the frequency of the wave, t is the time period of the wave. Both of these properties are common to the wave and the source. Omega is 2 pi f. Omega is called the angular frequency, as you probably remember. K is called the propagation constant, which is equal to 2 pi by lambda. Speed of a transverse wave on the string is given by V is under root T by mu, where T stands for the tension in the string and mu for the linear mass density of the string. Now, as far as longitudinal waves are concerned, in any medium, the speed of the longitudinal waves is V is under root E by rho, where E is the modulus of elasticity of that medium, so where E could be the Young's modulus or the bulk modulus. Now, a special case of this formula is the speed of sound in gas or air. Air is also gas, obviously. So this one, V is under root RT by M0, is the Newton's formula. Newton thought that passing of sound through air is an isothermal process, and hence he derives that the bulk modulus is P, and we get the formula V is under root P by rho, which is, well, slightly incorrect. So obviously, of course, later Laplace corrected this assumption that passing of sound through air is obviously not isothermal process but an adiabatic process. And so we have V is under root gamma RT by M0. We have done this derivation in thermodynamics as well, so shouldn't be a problem. And we get V is under root gamma P by rho as well. Rho obviously stands for the density of the gas in both of these formula. Alright. Okay. We have also seen that under some situations waves get reflected back, and when they do, it could either be inverted by 180 degrees from its phase or may not be. Now, based on that and based on the reflection, using the superposition principle, we derived 4 equations for things called standing waves. Hopefully you do remember that standing waves are those waves that do not propagate, so obviously they do not carry the energy forward like traveling waves do. So obviously equation of a standing wave is something of the form y is equal to 2a sine kx cos omega t, as compared to a traveling wave whose equation is y is equal to a sine kx plus or minus omega t. Okay. Now, we were discussing standing waves on a string, and we were considering the case when there is a node at both the ends. So hopefully you remember these diagrams. I'm just going to repeat these diagrams very quickly so that you can recollect what we have learned earlier. The first possibility for a standing wave on a string that's tied at both ends is as follows, which is obviously referring to the case that lambda is equal to 2L, or conversely f is equal to V by 2L. This frequency is also called the natural frequency of the string. The string's length is obviously L. So this frequency is the lowest resonant frequency. I repeat what I've said, this frequency is the lowest resonant frequency for this string. So for any frequency less than this one, less than this frequency, it is not possible to create standing waves on this string. I'll repeat what I've said. This is the lowest resonant frequency. For any frequency less than this frequency, it is not possible to create standing wave. on this string. Okay, the second case, again I'd insist that you all practice drawing these diagrams, because diagrams is definitely the best way to learn this. So here you can clearly see, based on this diagram, that this length is lambda and lambda is equal to L. So that obviously gives you the case where the frequency of this wave is going to be V by lambda, which is V by L. So what we are seeing is that we can create a standing wave that shows this pattern, or we could create a standing wave that shows this pattern. Obviously, I'm sure you do very easily understand what we should expect next. We should expect that there are 3 loops formed, as there are 2 over here and 1 over here. So obviously here you have lambda is 3L by 2, or conversely you have frequency of this wave as 3V by 2L. So what we have is, we can actually create a list of these frequencies, and all of these frequencies, they're combinedly called the resonant modes or resonant frequencies. So this is the lowest one, which is obviously called the natural frequency of this string. Remember, all of these are resonant frequencies. The lowest resonant frequency is the natural frequency. Now, what about these two? Do we have a name for these two? Yes, but actually we have a name for all the resonant frequencies. The first resonant frequency, the lowest resonant frequency, is the natural frequency. That's the name. The second one, the one corresponding to this diagram, this one is called the first overtone. You could actually remember it very easily, considering the word over, that indicates higher frequency. So this is the lowest resonant frequency. The next higher one is the first overtone, and the one next to it, this one, is the second overtone. And that is how things will continue. Now, so you can actually think of a very general case for the diagram of the nth overtone, right? So that's what we are doing now. Alright, so what I've got over here for you is a general diagram of some resonant mode and the corresponding frequency, NV by 2L. I'm sure you can easily recognize the pattern. The first frequency, the first resonant frequency, which is the natural frequency, is 1V by 2L or V by 2L. The next one, which is called the first overtone, is 2V by 2L or V by L. The third one, which is called the second overtone, is 3V by 2L. So you see the pattern: 1V by 2L, 2V by 2L, 3V by 2L, and so on. Alright. So the general case is F is NV by 2L. Now, if you consider this diagram, I want all of you to figure it out. What is the frequency in which this string is vibrating? And the answer is actually pretty simple. If you just count the number of loops, okay, 1, 2, 3, and that actually means that this is going to be 3V by 2L, where L is the length of the string. Now, that's because for the first one, if you see the diagram that we have drawn before a while, you realize for the first one you have one loop and it's V by 2L, and second one 2V by 2L, and so on. Alright, now here I've marked a few points, nodes and antinodes. Well, hopefully you do remember that nodes are those points that do not have displacement while the string vibrates. Basically, nodes are points where the amplitude of the standing wave, this is the amplitude of the standing wave, is 0. So here it's 0, here as well, here as well. So these points are nodes. Now obviously between two consecutive nodes you have an antinode. That's due to the property of sine. Between 2 points where sine's value becomes 0, you're going to get one point where the sine's value will either become +1 or -1. So 0 over here, 0 over here, 0. Alright, nodes. And here it's either plus 1 or minus 1. Again, over here 0 and 0, so between the two it's either plus 1 or minus 1. So wherever that happens, the point becomes an antinode, and we also have an antinode here. So in this diagram, what we are seeing is that there are 4 nodes and 3 antinodes, right? Between 2 consecutive nodes there is an antinode. Now you can also easily see that the distance between 2 consecutive nodes, or antinodes for that matter. Alright, so let's see what's the distance between 2 consecutive nodes or 2 consecutive antinodes. If you have a look at this carefully, you would realize that this distance is equal to half of the wavelength. This is one wavelength, cut it into 2, so you have half of a wavelength over here. Now that means the distance between these 2 nodes is lambda by 2. That's correct. Same over here. Similarly, the distance between these 2 antinodes, obviously because they are symmetrically located, is also lambda by 2. So the answer to this thing, distance between the 2 consecutive nodes or antinodes, is lambda by 2. Now that's fixed. This does not depend on which frequency or which resonant mode the string vibrates. But obviously what happens is that although it looks like this distance does not depend on anything, well, it depends on lambda, and lambda depends on frequency. So indirectly the distance between 2 nodes does depend on this frequency. So that's something which you should be careful about. Alright. Now I'm going to ask you to have a look at the video which is linked over here in the description, because that video is very important for you to understand how a string on which there is a standing wave oscillates. I've shown this video to you in the class, but I'm not so sure you'd be remembering it, so I want you to see it again. The link is in the description below this video. Now we're going to study how phases of different points vary in a standing wave. Now I'd like all of you to recall that for a traveling wave, if you consider this string, and let's say there is a traveling wave on this string which is traveling towards the right side. So every point on this string will have a different phase. So that is a unique property of traveling waves. On the other hand, for a standing wave, we've got something very interesting going on. So let's say we consider that we have a standing wave on a string in the first overtone, so that there are 2 loops formed over here. Here's a node, here's one more, and here's the third one. The length of the string is obviously L again, this being half of the wavelength. So here we have an antinode, and here we have an antinode. Now I hope that before we move forward, you have observed carefully what happens to the string in the video linked in the description. Alright. So you would have noticed that when the string vibrates in the first overtone, when this point of the string reaches here, it has maximum displacement obviously. At the very same time, this antinode doesn't actually go up, it goes down. So what you are seeing is that this part of the string goes up while this part of the string goes down. Now what that means is that if I consider points number 1, 2, 3, and let's say 4 and 5. So what happens is that the points 1, 2 and 3, they're all going up at the same time, but at the same instant you are going to see that 4 and 5 aren't going up, they're actually going down. So what is happening is that 1, 2 and 3, they all move together, 4 and 5 go down together again. So when 1, 2 and 3 will reach their own amplitudes, now I'm saying their own amplitudes because amplitude is not same for all. Let me make you recall again. For a standing wave, the equation is something like this, and you can clearly see that this thing which is called the amplitude depends on x, that is the position. Now, so the points 1, 2 and 3, they don't have the same amplitude, but that's not the point really. The point is that all the three will reach their amplitudes together, in phase, together. There is no phase difference between 1, 2 and 3. Hello everyone. Today we are going to solve a few questions about standing waves on strings. So here's the first one. This is question number 11 from the exercise of the textbook. As you can see, the data says the transverse displacement of a string clamped at both ends is given by y of x comma t is 0.06 sine 2 pi by 3 x cos 120 pi t, where everything is in SI units. The length of the string is 1.5 meter and the mass of the string is 3.0 into 10 raised to minus 2 kg. Question says, answer the following. A. Does the function represent a travelling wave or a stationary or a standing wave? Well, obviously, have a look at this equation. This does not match with y is equal to a sine omega t minus kx, which is equation of a travelling wave. Instead, this equation matches with this. So when we do a comparison, it is quite clear that this is the appropriate form, and hence this must be the equation of a standing wave or a stationary wave, not a travelling wave. So the answer to A is it's a stationary wave. Now B, interpret the wave function as a superposition of two waves travelling in opposite directions. What is the wavelength, frequency and speed of each wave? Alright, so hopefully you do remember that when a wave hits an end, gets reflected back, what happens is, due to the superposition of these two waves, that is the incident wave and the reflected wave, we have a pattern. We have a pattern of nodes and antinodes. We have standing waves on the string. Now, the idea here is that we are going to decompose, we are going to split this equation into two different equations, both of them of travelling waves. Well, that is very easy by using a little bit of math formula. Well, we can easily compare it with an equation of this kind that you have studied. We are going to use the equation of, if you write it like this, y is 2 sine alpha cos beta. So that allows you to easily say that if we write 2 sine alpha cos beta and we put it in form, right, so we are going to get 0.03. notice this, because the 2 goes with the formula. Sine alpha cos beta obviously becomes sine alpha plus beta, so that is, you have 2 pi by 3x plus 120 pi t plus sine alpha minus beta, so that is going to be 2 pi by 3x minus 120 pi. So thus we have decomposed, we have split this one equation of standing wave into two different equations for travelling waves, as you could see. So one of the travelling wave is going to be 0.03 sine 2 pi by 3x plus 120 pi t, and the other one is going to be the one with a minus sign. Okay, so what we have done here is, you need to realize that these are the these are the two travelling waves that make this standing wave, right? Okay, the third part. C, determine the tension in the string. Now this one I'm going to leave it for you. You can see, you can analyze the equation of this travelling wave, and I'm sure you can easily find out quantities like k, the propagation constant, and omega. Now once you find out what is k and what is omega, finding v, the wave velocity, should not be a problem. And then that is how you can find out the tension in the string using the length of the string and the mass of the string. Alright. Now there's one more question that we could do here, and that is question number 14 from the same exercise. So that's what we're going to do in a moment. Alright, so let's get started with question number 14. I have the essentials of this question on the board. Let's have a look at all of these again. Question says, a wire stretched between two rigid supports vibrates in the fundamental mode. So as you can see, I've drawn a diagram of a standing wave on this string, and clearly this shows the fundamental mode because it has one loop. So the fundamental frequency is 45 Hertz. Alright, mass of the wire is given, the linear mass density of the wire is also given. We have to find speed of the transverse wave on the string and tension in the string. So we are required to find speed of the wave on this string, and we have to find what is the tension in the string. Alright, so now if you figure out what's the relation between these things, I'm sure you won't have a problem. For example, try to recall the formula of the fundamental frequency. The fundamental frequency F is given by V by 2L for a stretched string. Now if you have a look here, we know what's the value of F. We don't know the length, and this is what we have to find. But there is a way to find out length. As you can see, mass of the wire is given and the linear mass density is given. So using that, I may write that the length is equal to mass divided by the linear mass density. Right, you could verify that very easily, as we have mu is mass divided by the length, so length is m upon mu. Alright, so if we put it here, we get v into mu upon 2m. Alright, so that's how you could easily find out the value of speed of the wave on this string. Right, you can put the values of f and m and mu. Alright, now the part B of the question says find out the tension in the string. Well, this is same as what we did in the previous question, the number 11 question, so I'm not going to repeat it. I'll leave it for you. Alright, now we are going over to question number 12 from the exercise. It says, for the wave on a string described in exercise question 11, that is the previous question which we have done, obviously about standing wave. So the question says, do all points on string oscillate with same frequency, phase and amplitude for a standing wave? Okay, so what we have to decide first of all is that in the previous question the string was vibrating in which mode. Remember, we are talking about question number 11. Alright, so as far as question number 11 is concerned, we're going to have to find out which mode it is vibrating in. Now I'm only going to give you hints over here. See, the idea is that if the string vibrates in fundamental mode, you can see that hopefully you do remember the explanation that I gave you in the previous class. You see the points 1, 2, 3 and 4, they are all located between two nodes, two consecutive nodes. So when 1 is going to reach its amplitude, so will 2, so will 3, so will 4 and so will this anti-node point. Now that means that all of them go up together, they reach their amplitude, they go back. That means they are all in the same phase. But that would not be the case for any of the higher resonant modes. Have a look here. So let's say points 1, 2 and 3 are located like this. So 1 and 2 are in the same phase but 3 is not. So the answer to this question, are all points in the same phase? depends on whether it's the fundamental mode or not. So that's what you'll have to check from the question 11. I'm leaving that part as an exercise for you. Okay, as far as frequency is concerned, a frequency, that's very easy. As a wave travels, all the points on the string or in any medium, they always oscillate with the same frequency as the source. So you do remember that frequency does not depend on the medium, only on the source. So that's why 1, 2, 3, 1, 2, 3, 4, 5, everything, they're all going to vibrate with the same frequency. So the answer to the question A is yes, same frequency. B, it depends, that's what you have to figure it out. And amplitude, well, if you have a look carefully at the equation y equals 2a sine kx cos omega t, I'm sure all of you have easily realized that the amplitude in a standing wave depends on x, that is the position. You can see that over here as well. There are nodes which have zero amplitude, and then there are antinodes which have maximum amplitude. All these points in between them have different amplitudes. So the answer of C is obviously no, different amplitudes. Okay, now explain your answer as well. It's all done. What is the amplitude of a point 0.375 meter away from one end? Again, we're going to refer to the question 11, right? So I'm going to write down the equation again. The equation for question 11 is y is 0.06 sine 2 pi by 3x cos 120 pi t. All right. So the first thing is to identify the amplitude. This is the amplitude. Again, amplitude depends on position. So if we take this end as x equal to 0, which says, which agrees with what it says, what is the amplitude of a point 0.375 meter away from one end? So from here. Alright, so that is what you could put as x. So what I'm going to do is to find the amplitude a dash. I'm going to write a dash is 0.06 sine 2 pi by 3 into x, where x is 0.375. Alright, so then all you have to do is multiply this out, use your trigonometry tables if required, and get the value of this amplitude, and that's all. Okay, so the next topic that we are going to talk about is propagation of sound or any other longitudinal wave. Now, what I've drawn over here is an indication of the phenomena that occurs while sound passes from this source towards this observer. Right? So let's say there's a person listening to the sound produced by a speaker over here. So what happens is, when sound is produced from this end, it passes as a series of compressions and rarefactions in air. Obviously, compression is getting smaller in volume, and rarefaction is opposite, that is getting larger. So compression obviously comes with an increase in the pressure above the equilibrium pressure. So you see that if there was no sound passing through this air right now, its pressure would be the equilibrium atmospheric pressure about 1 atm. When I speak, that creates pressure pulses. So the pressure at this point might be a bit more than 1 atm, and then the next region, the next zone, which would be a rarefaction zone, there you'd have the pressure slightly less than 1 atm. Again, there are alternate compression and rarefaction zones. Now this is pretty much the same as the shape of a string. When the string has transverse oscillations, at any point of time, a part of string has risen up above the equilibrium position, while the next part has gone below. Well, here, because this is a longitudinal wave, so the particles of medium, they don't go up or down. Instead, they move back and forth. So what happens is that as sound will pass, particles will oscillate. Now if particles come close towards one point, that's where you have the compression zone. Now when the particles go away, That's where you have the rarefaction. So that is how, by alternate higher pressure, lower pressure, higher pressure, lower pressure zones, you have sound passing from one point to another point, from source to observer to air. Now, although this explanation is about sound passing through air or a gas, but the truth is that this is true for all longitudinal waves, even sound wave in a bar. So that's why this serves as a general purpose example for explaining longitudinal waves. Alright, so the mathematics is pretty much the same, just like you'd have the equation y equals a sine omega t minus kx for a wave traveling towards the positive x direction. Now the same thing, same kind of equation is true for a pressure wave or a sound wave. So that would look like this. Again, this plays the role of amplitude. So what I've marked here is this is the positive amplitude and this is the negative. So the change in pressure for any point is going to be delta P0, that is the amplitude, the same role as A, and then so forth. Alright, so this is what a pressure wave looks like. Now interestingly, sound wave can be understood to be both, or in both ways. That is, either as a displacement wave where we talk about the particles going back and forth, or as a pressure wave where the pressure in one zone is higher and then in the other one it's lower, and so on. So which one is better for us? Which one is more useful? Well, the answer to that is the pressure description, the pressure wave description, because our ears sense the change or variation in pressure. Our ears do not sense the variation in position of air particles, and hence we are always going to talk about sound wave as being a pressure wave. I repeat, we will always consider the sound wave to be a pressure wave unless explicitly mentioned. Alright, so keep that in mind. Okay, so now we are going to talk about standing waves occurring in organ pipe. Now if you go back, recall that there are traveling waves on a string, and then when the wave reflects you could have superposition of waves, and then you get standing waves on a string. Well, more or less the same kind of phenomena occurs for for waves of sound, and that also produces standing waves, standing sound waves. Okay, so let's have a look here. So first of all, we are going to talk about how standing waves occur in an open organ pipe. Well, what's an organ pipe? Well, it's anything cylindrical shape and which could resonate or produce a sound. Now we are going to study about two kinds of organ pipe. Here's the first one, the open organ pipe. Now what I'm going to say might sound pretty obvious, but it's necessary that I make it clear. An open organ pipe is something that is open at both ends. That is something I don't want you to forget. Remember, open organ pipe means a pipe that is open at both ends. So it's open here and it's open here as well. The diameter is not of much consequence at this stage. Let's say the length of the pipe is L. Now what I want all of you to realize is, have a look, at these 2 points we have nodes. Why? Well, the explanation is that this point is in direct contact with the outside atmosphere. Now you can't change the pressure of the whole atmosphere, that's not possible. So whenever a wave is traveling inside this, the pressure at this point must remain the same as the outside pressure, that is the equilibrium pressure or the atmospheric pressure, and hence at this point the pressure cannot change. Now this is the same as if you consider a string which is tied at both ends. You have two nodes, that's fixed, you can't change those. You have two nodes at both ends because it's clamped, so it can't move, there's no displacement. Same thing here. There can't be any variation or any change in pressure. Again, if you go back and compare the two equations of waves, well, I'm not writing both of those again, but I'm sure you get the idea. They're pretty much the same. So displacement, change in pressure, same rho. So here you can't have displacement of this point and that point, so they are nodes. And here you can't have change in pressure at this point and change in pressure at this point. You have a node at both of these points. So this is something worth remembering. At open end of the pipe, at open end of the pipe, there is a pressure node. This is something that you should remember. At open end of the pipe you have a pressure node. So this is going to behave in pretty much the same way as a string behaves. String has nodes at the end points, and open pipe has nodes at the end point. So now what's going to happen is that every property that we saw for standing wave on a string is going to repeat itself for a standing wave in open organ pipe. So that's good news for us. You can just use one of the information, one of the understanding, and apply it easily onto the second case, onto this case of waves in an open organ pipe. Okay. So let's see what the equations will turn out to be. Again, obviously the fundamental frequency or the natural frequency is going to be F0, which is once again going to be V by 2L, and all the resonant frequencies are going to be NV by 2L, where again N is 1, 2, 3 or any other higher natural number. Now if you want to draw diagrams, well, they look the same as they did in the case of standing wave on a string. But here I want all of you to recognize that although we have drawn it like this, there is nothing that's actually going up. You would have seen in the video that I linked in the previous class, that the string would go up and then it would go down, but here air doesn't go up and down like that. So what is this diagram for? Well, this is more like a graph. It's a graph of pressure variation. Over here there is zero pressure variation, so it's a pressure node. Over there again zero pressure variation, it's a node. And over here at this point right here in the middle of this pipe, you have maximum pressure variation possible, and that's why this point is nothing but the anti-node. That's something you should not forget. Alright, now we are going to talk about the second case of the organ pipe, that is a closed organ pipe. Well, what's a closed organ pipe? Again, it's pretty obvious, but I still have to mention it. Open at one end. The organ pipe is open at one end but closed at the other end. Warning, closed pipe does not mean closed at both ends. That's not how we are going to produce sound from an organ pipe. So remember, it's open at one end, closed at the other end. Now what we have here is, well, this end is open, the length is L, alright, so this end is definitely a pressure node, as we talked about it before a while. So this end is a node. Now what about the closed end? That's something very interesting. What happens is that when sound wave travels all the way there to this point, to the wall, remember it's closed, there's a wall. So what happens is sound can't go through. The pressure over there will be maximum. I'll repeat what I've said. At the end point, the molecules can't move. So what happens is, when the previous zone, the molecules of the previous zone or this one, they move towards the wall, that's it. The pressure over there will increase, and hence it is necessary that at this end you have a pressure antinode. So to sum it up, I'm going to write it here, that closed end of pipe is a pressure antinode. That's the main thing. Closed end of the pipe is a pressure antinode. So now this situation is different from the standing waves in a string, or different from standing waves in an open pipe. So that's why we are going to analyze it very carefully. Again, if you want to understand the concepts like fundamental frequency, resonant frequencies, nodes and antinodes, it's best to draw a diagram. So I'm going to start with the first case, right? So here's the first case. This is case number 1. Here I'm going to draw it for fundamental frequency. Rules, well, this is a node, this is antinode, pretty clear. So what I'm going to try and draw is I'm going to make a node here and an antinode over here, and there we go. Alright, so this is what the diagram will look like. Again, don't forget, this is not an indication of air moving like this. No, that's not what we are saying. This is just a graph of pressure variation. Here there is zero pressure variation, it's a pressure node, and here there is a maximum pressure variation, it's a pressure antinode. Now if you would take this graph out of this pipe, I'm sure you'll easily understand what we are drawing here. So I'm going to take this graph out of this diagram of the pipe, and we are going to analyze it carefully. So here we want it to be an antinode. So you can see that till this length it's actually half of this loop. I hope you get what I'm saying. Till this point it's half of this loop. So what we have is, I'm sure you do recall from standing waves on a string, that one loop is lambda by 2. I repeat, this one loop's length from all the way from here to here is lambda by 2. So the half of it, half of that length, that is only till here, should correspond to half of that, that is lambda by 4. So what we have here is effectively this length L of the pipe matches with lambda by 4, where lambda is the wavelength of the sound wave produced inside this pipe. So what happens is that this length L is, well, lambda by 4. That is what happens in the first case. I'm sure you do realize that there is no other case, no smaller case possible. Anyways, you are going to understand that even better as we draw the second one or the third one. Anyway, so L is lambda by 4. So that gives me that lambda is 4L, and finally that gives me the formula of fundamental frequency of this pipe. Remember, it's the first case, so it's the fundamental frequency. So the fundamental frequency of this closed organ pipe is given by F is V by lambda, and lambda is 4L. So that gives you the formula of fundamental frequency of a closed organ pipe. It is F0 is V by 4L. So remember that fundamental frequency of a closed organ pipe is V by 4L. Okay. Alright, now we are going to talk about case number 2. That is the second resonant mode of an organ pipe. Remember, we are talking about a closed organ pipe which is closed at this end but open over here. So again, there is pressure node, there is pressure antinode. Don't forget that at the closed end you have a pressure antinode. Okay, so time to draw diagram. Now this is where you have to be a bit careful. So if you consider this very carefully, this is what it would look like. Remember, we should have an antinode over here and a node over here. So that is only possible like this. Obviously this is the second case. We have already discussed the first one. So this is what it would look like. Well, it looks like fishes to me, very frankly. So, well, we have one loop and one half of a loop. Again, the length of the pipe is L. The length of this loop should be, well, lambda by 2, and as you can clearly see that this part is half of this one. So this length is lambda by 4. So effectively here we have L, the length of the pipe, as lambda by 2 plus lambda by 4, which I'm sure you understand easily is 3 lambda by 4. Okay, now that gives us lambda is 4L by 3, and that gives us the frequency of sound in this case is F is V by lambda, which is going to give us 3V by 4L. Okay, that's a surprise. If you have a look carefully at the fundamental frequency, it is V by 4L, and now this one is not 2V by 4L, but it is 3V by 4L. So you can see we are picking 1 and then it's 3, not 2. Now you'd get this better if you go to the next case, and let's draw the diagram once again. So let's say there is a pipe again of length L. Now this is where I'd like all of you to try it yourselves in your notebook. I'm drawing diagrams here on the board, but the real challenge is to get the number of loops correct. First case, fundamental frequency, just 1/4 of a loop. Second case, this one loop, and then again half of it. Sorry. And now, okay, like this, and then, well, it's not perfect, but it will do its job. Okay, so this is what we have. So this is again lambda by 2, this is lambda by 2, and this is lambda by 4. The total length of the pipe is L. Okay, this end is closed, must be a pressure antinode. So finally you're going to get L is 5 lambda by 4. Lambda by 2 is lambda, and lambda by 4, so 5 lambda by 4. Effectively that means that F is going to be 5V by 4L. I'm sure you can do the math yourself. So what we have is, now you're seeing a pattern. The pattern, I'm sure, is very clear. It's the odd numbers. So fundamental frequency is 1V by 4L, the next resonant frequency is 3V by 4L, and the next resonant frequency is 5V by 4L. What this means is we are only getting the odd numbers. So as it was the case for strings, we have these nomenclatures for overtones here as well. So this is the first overtone. So the first overtone frequency is not 2V by 4L but 3V by 4L, and the second overtone frequency for closed pipe is 5V by 4L. Now the general case is going to be, okay, I'll write it over here, general for resonant frequency for closed pipe. Because we are taking odd numbers, I'm sure you have studied this in your 10th standard maths course, that for odd numbers you should either use 2n plus 1 or 2n minus 1. Those give you the odd numbers. We are going to choose 2n minus 1, so that you can start with 1. So it is 2n minus 1 V by 4L. Again, if you put n is 1, you get 1V by 4L, which is fundamental frequency. If you put n is 2, you get 3V by 4L, which is the first overtone over here. Okay, so don't forget this formula. It will help you solve many problems. So we are done with standing wave theories as far as pipes are concerned. Again, open pipe, open at both ends, and an open end is a pressure node. A closed pipe is open at one end but closed at the other end. That's why it is called a closed pipe. Now, closed end is a pressure antinode, and that is the basics of drawing all these diagrams. The fundamentals remain the same. The basic idea is just the same. Once you know what's the wavelength based on this diagram, it's very easy to calculate what is the frequency. Okay. Now we're going over to one topic, one common thing that connects all these, the string, the open pipe, the closed pipe, and that is harmonics. Now it's worth knowing, worth remembering what is harmonics and the difference of harmonics with overtones. Be very careful. Right. So let's start with harmonic. What is harmonic? We are going to define it first of all. So a harmonic is, or are plural, they are the integral multiples of the fundamental frequency of maybe the string or pipe or any other thing that may show these kind of phenomena. Now that actually means if I make a list of harmonic, this is how it will work. Well, let's see. So here is fundamental frequency, okay, which is obviously also the first harmonic because it's the first multiple of fundamental frequency. Now we are going to talk about the higher harmonics, and I'm sure you'll get the idea. So let's say we have the second harmonic here, the third, and so on and so forth. And now I'm going to characterize this. I'm going to explain each of these separately for string, open pipe, OP stands for open pipe, and a closed pipe. Okay, so let's get started. Now first of all, fundamental frequency of string, I hope everyone remembers, is V by 2L. L is length of the string. Same story here. Okay, for a closed pipe the fundamental frequency is V by 4L. Second harmonic is going to be 2V by 2L. Again, second harmonic itself means second multiple of fundamental frequency. Third harmonic itself means third multiple, that is 3 times the fundamental frequency, so it is 3V by 2L. Remember, we are talking about the string. But for an open pipe there is absolutely no change here, because again this into 2 is 2V by 2L, this into 3 is 3V by 2. But obviously for a closed pipe it's going to be different. So you can see for a closed pipe you have the second harmonic as 2V by 4L, and here you have 3V by 4L. So this is the part of the table that will bring out interesting details. Have a look here. Fundamental frequency, first harmonic, fundamental frequency, first harmonic, fundamental frequency and first harmonic. No surprises. Here second harmonic is 2V by 2L, which is V by L. So you can see, if you recall, first overtone, if we talk about a string or an open pipe, the first overtone is V by 2L. So for a string or an open pipe, the first overtone itself is the second harmonic. Okay, now if you look at the third harmonic, it is 3V by 2L, which is the frequency of the second overtone. Look at your notes. Second overtone frequency for string or open pipe is going to be 3V by 2L, because the formula is NV by 2. So what we are seeing is for string or open pipe you have this kind of relation. So based on this, I want all of you to be able to answer basic questions like, suppose you are going to talk about third harmonic of open pipe, then that is the second overtone, and you should be able to draw the diagram, find out the formula, etc., etc. So fourth harmonic of the open pipe or the string is going to be the third overtone. But the situation is slightly complicated for the closed pipe. Look at the second harmonic. It's 2 is cancelled, so V by 2L. Second harmonic V by 2L for closed pipe. Well, that's not an overtone frequency. I hope you got what I said. It's not an overtone frequency. The second harmonic is V by 2L. So for a closed pipe, is V by 2L first overtone? The answer is no. So the second harmonic is not first overtone. So this is true for string or open pipe, but the same thing is not true for a closed pipe, right? So but if you go to the third harmonic, 3V by 4L, you can see this is the frequency of the first overtone. So for a closed pipe, we have slightly strange things going on. It's that the first overtone is same as the third harmonic, not the second harmonic. So if you continue the pattern in same way, what you'd have is the second overtone will not be the fourth harmonic, it will be the fifth harmonic. I'm sure you guessed that, because we are going to have 5V by 4L. 1V by 4L fundamental, 3V by 4L first overtone. Okay, 5V by 4L is the the second overtone. So what we have is the second overtone for a closed pipe is going to be the fifth harmonic. Now what we have over here leads to two important sentences. That's what I'm going to write. We are going to talk about the relations of harmonics and overtone. So first of all, for strings or open pipes, the relation is very simple. It is that all overtones are harmonics. Well, this is something that is always true, but the converse is also that all harmonics are resonant frequencies. So what this means is you can pick any harmonic that you want. Let's say the third harmonic, which is going to be 3V by 2L, 3 into V by 2L. It's going to be a resonant frequency. In fact, it's the second overtone, 3V by 2L for open pipe or a string. So that's what these sentences tell you. So here the relation is fairly simple. But if we go to closed pipe, the relation, I'm going to write it in a moment, but let me just explain over here so it's very clear to you the moment you read it. What we have seen is that for a closed pipe, V by 4L is fundamental frequency. Then the first overtone is 3V by 4L. Excuse me. So what we have is V by 4L is the fundamental frequency, 3V by 4L is the first overtone. But you could see the second multiple, the second harmonic is missing. There is no 2V by 4L. After 3V by 4L, the next resonant frequency is 5V by 4L. Again, you can see we have skipped over the even one, that is 4V by 4L. The fourth multiple, the fourth harmonic is missing. So this is what allows us to write these sentences. Obviously, all overtones are harmonics. There is no surprise about that. But what we have is only the odd harmonics are resonant frequencies. Only the odd harmonic are resonant frequencies. So 1V by 4L is a resonant frequency, 3V by 4L is a resonant frequency, and so is 5V by 4L and 7 and so on. But you don't have 2V by 4L as a resonant frequency. So that's the importance of this sentence. Now I'm just going to give you a little practice to find out the harmonic and the overtone in case fundamental frequency is given. Okay, here is the practice question for you. Suppose there is an open pipe whose fundamental frequency is 100 Hz. You have to tell me that 300 Hz would be which harmonic and also which overtone. Well, the way to analyze this situation is, well, there is 100 Hz, 300 hertz. Recall the definition of harmonic. It is the integral multiple of the fundamental frequency. 100 is the fundamental frequency. If you multiply it with 3, you are going to get 300 hertz, so it's the third harmonic. Now, which overtone? So for that, you are going to have to consider what this is. It's an open pipe. For an open pipe, 3 times fundamental frequency is 3V by 2L, which is the second overtone. So the correct answer to this question is it's the second overtone. I hope that is clear. Now we are going over to the closed pipe, and the fundamental frequency is 150 hertz and 600 hertz is which harmonic? Well, that part is fairly clear. I'm sure you understand. It's fourth harmonic. And which overtone? So the answer is it's not an overtone, because if you read those sentences, we have seen that the first harmonic is the fundamental frequency for closed pipe, the second harmonic is nothing, the third harmonic is the first overtone, and again the fourth harmonic is nothing. So fourth harmonic is not an overtone or not a resonant frequency, and hence the answer to this question, 600 hertz, is which overtone? The answer is not an overtone. Okay, 750 hertz, I'm leaving that one for you. Okay, so we are now going to solve a question related to standing waves in this object. The question number is 16 from the exercise of the textbook. Okay, the question says there is a steel rod 100 centimeter long, is clamped at its middle. It's being held, it's clamped, it's fixed over here. So one thing is quite clear: if it's clamped, it's fixed over here, this point must be a node. That's correct, node. Alright, now the fundamental frequency of the longitudinal vibrations of the rod are given to be 2.53 kilohertz. So we are given that when we allow this rod to vibrate, it's going to have a fundamental frequency 2.53 kilohertz. That's, well, nothing but 2530 hertz. We now have to find what is the speed of sound that is longitudinal waves. We have to find what is the speed of sound in this rod, in the steel rod. Okay, well, so the first thing to do over here is to draw a diagram for standing waves, because fundamental frequency is mentioned. We are going to draw a case of the fundamental frequency. I'm just going to extend these out here. This point is a node. Now the first possible case for resonance, I'm sure you understand, should look like this: node over here and antinodes at both ends. So what we have is that this distance, as we have seen earlier, it's half of a loop, is lambda by 4, and this distance again is lambda by 4. So that gives us that the whole length of the rod L is lambda by 4 plus lambda by 4, that is lambda by 2, and ultimately we can find out the speed of the sound in this rod easily by using this formula. Well, F0 is given, lambda we can easily find from L, so lambda is going to be 2L, and that gives you the value of V after you substitute value of F0 and length obtained from here. Alright, so that's how we have to solve this question out.